Good morning, students. So this is our second meeting here through video, and I hope you had time to look through the video that we uploaded on Tutor plus the PowerPoint. So today what we want to talk about is one-sided limit. And straight away we want to start with an example of a heaviside function, which is defined to be 0 when t is less than 0, and also is defined to be 1 when t is greater or equal to 0. And you can graph this function easily because now you know piecewise function from our algebra. So suppose this is your 0 here at the origin, then we have 1 here. You can put other points, but these are of interest looking at how our function is defined. So at 0 here we have a point with a hole, and then this is the graph of the function where it is 0 when t is less than 0. So it's all over the t-axis. And remember also the function is 1 when t is greater or equal to 0. So that means at x, which is equal to 0, we have our point which is included here, and then when t is greater than 0, our function remains at 1 all the way. So one thing which we can see looking at the graph and also looking at the function, the way it's defined as a piecewise function, you can see that as t approaches 0, from the left the heaviside function goes to 0. So when t gets closer to 0, but from the left the heaviside function goes to 0. And as t approaches 0 from the right, our function, the heaviside function, approaches 1. We can write what we have just said in terms of a new notation that we are introducing now. So we are introducing the limit of the heaviside function as you approach 0 from the left. So we denote that by a minus sign, a superscript of a minus sign on 0 here. So you can see the superscript of a minus sign. A heaviside function becomes 0 as you approach from the left. So whenever you see this minus sign as a superscript of the point that we are trying to approach, it means we are approaching from the left. Whenever you see the plus sign, it means we are approaching from the right. So you can see the plus sign here. So it's t approaches 0 but from the right. So that's what you have to bear in mind. That's what we are going to use as we go along. And we call these one-sided limits and this one is the left side limit, this one is the right side limit. So keep that in mind as we go along. And we can also indicate that to say whenever the t approaches 0 with a superscript minus sign, that indicates we are looking at the values which are less than 0 in this case, and then we approach 0. We come as close as possible to 0. And whenever we have t approaching 0 with a plus as a superscript, then it indicates that we only consider values that are greater than 0 in this case, and then we are trying to approach 0. So keep that in mind. Keep that in mind as we go along. So now we can talk about some kind of a definition of the one-sided limit. That whenever we have this limit of f of x being equals to L as x approaches a from the left, we can also say the left-hand limit of f of x as x approaches a is equal to L. That's one thing we can say. And we can do the same for the right hand limit, where we say the limit of f of x is L as x approaches a from the right. Or we can write it as the right hand limit of f of x as x approaches a, but remember we are approaching from the right, is L, is equal to L. That means we are try as x gets as close as possible to a, but from the right, then the function gets to L, or the behavior of the function, the values of the function, they get as close as possible to L. So these are the two parts of the decided limit, left and right. Keep that in mind as we go along. And we can put it here to say, suppose we are approaching, we say x goes to 5 from the left. That means we are only considering values of x which are less than 5. Or if we say x approaches 5 from the right, it means we are considering only values that of x that are greater than 5, but that are in the neighborhood of 5, close as possible to 5. Or you can put it in terms of the graph to say the limit of f of x is L as x approaches a from the left, to mean your as x approaches a from the left, f of x goes to L. Or you can say from the right, the limit of f of x as x is L as x approaches a from the right. In this way, what are we saying? We are saying as x approaches a from the right, f of x will approach L. So there we go. So you can see it graphically that even from the graph you can be able to deduce the decided limit, or be able to tell the decided limit just looking at the graph. So now we can come to the definition that we gave in the previous video to say, remember we talked about the general limit in the previous video. So we are saying the limit of f of x is L as x goes to a, if and only if, that is a very important statement, both sides limit exist and they are the same. So it means the left side limit as x goes to a from the left of f of x is L, and also the right side limit is also L. So they exist and they are the same. So the if and if part here, we'll use it most of the time. If we say if and if, we mean if this statement is true, it implies the other statement. That means it will imply that the sides limit exist. And also if the sides limits exist, both of them, it will imply that the limit exists. So that is a kind of a double implication, of which later we may use, instead of if and if, we may use a double implication like this. So we are introducing them one by one as we go along. So that's the statement you have to get in mind, that if this portion is true, then this one, the limit exists as of f of x and is L as x approaches a. And also if the limit of f of x is equal to L as x approaches a, then it means the decided limits exist. I hope you get that in mind. So now let's look at this good example that we have here, where you are given a graph and you want to deduce some limits looking at this graph. So the first one, number A, it says the left hand side limit of g of x. That means sx goes to 2 from the left. So we'll go to the graph and try to approach 2 from the left. So it's 2 from the left, and you can see these are the values, and then you get closer to 2 from the left. You find that your limit is nothing but 3. So we can straight away conclude that as we approach 2 from the left, the limit is nothing but 3. What about number B, when you approach 2 from the right with the same function g? So let's approach 2 from the right, start from the right, and then you get the function, and then you get close again. So you find that when you approach from the right, although my drawing is bad, actually I should have touched the graph here. When you approach from the right, you'll find that you are getting the limit of the function is 1 in this case. So that means in this case we have the limit of the function to be 1. Now C is a conclusion now. Remember the previous conclusion that we made of the definition, that if the two sizes limits exist and they're the same, then we conclude that the limit exists and will be what we get from the sided limit, which will be 1 value. But in this case, we can see we have 2 values which are different. The left side limit is 3 and the right side limit is 1, and they're different. So straight away here for C, we can conclude that the limit does not exist. So in this case, we can conclude that does not exist because the two sizes limit are different. If they were the same, we'll conclude that it exists, and then it's exactly that limit that we get from the sided limit. So this goes to number C. What about number D? Number D, you try to approach 5 from the left. You approach 5 from the left. So if we get that value, you'll find that you're getting closer to 2. And then even if you get closer, you will get closer and closer to 2. So from the left, actually, remember you are not at x is equal to 5. You come as close as possible, but don't get to x which is equal to 5. And you can see for this function that for x which is equal to 5, the value of the function is not 2. So for number D, we'll conclude that as we approach 5 from the left, the limit is 2. Okay, good. Let's approach the same from the right. If you approach from the right, you try from far and then you get closer. You find that even from the right, with my bad drawing, as we get closer, you find that you are getting closer and closer to 2. So from the right is also 2. That's what we deduce from the graph. And in this case, with the same definition that we had previously. Now that the left side limit and the right side limit exist and they are the same, then you can conclude that the limit f, you don't need even to work it out, is nothing but 2. So the limit of g as x goes to 5 in f is nothing but 2. So for this one, you don't need to waste time because you've already computed the sided limit and you'll find that they exist and they are the same. So you can conclude the limit as we approach 5 of g of x. That's it. So I hope with this example you are able to grasp the sided limit, and it gives an idea of how to move from the sided to the general limit, where you're not considering the sided limit, or you have the general limit, now you are moving to the sided limit. So this is a very good example. And these are just the answers that we have just seen. One thing which we talked about, we said even though the limit, we have found the limit, we noticed that g when x is equal to 5 was not equal to 2. But that is not the problem, because we don't care what happens when when x is equal to 5. We don't care about the behavior of g at that point. So that's one thing which we notice from the graph. So let's stop here, and next time when we meet, we would like to look at how can a limit fail to exist. We have already seen examples of how the limit fails to exist. One of them that we have seen previously is where the two sides of the limit are different. So we want to look how the limit failed to exist, look at other options that can make the limit not to exist. So it's not only when they are different. So next time you will see, or yes, we'll go along with the material in my absence. I know some of you have already moved forward to the ends of the presentation. So as we continue, you will see some of the things that you never thought that they will come out to tell you that the limit does not exist in this case, but we'll see it next time. So what can we say we learned today? Today we have learned the notation of sided limit, that we can use a plus and minus sign to denote the sided limit. In fact, we said we can use the minus sign as a superscript of the point that we are approaching from the left to show the left hand limit. And also we can use the plus sign as a superscript to the point that we are approaching to denote that we are approaching that point from the right. We have also learned that if the two sides of limits exist and they are the same, it implies that the limit at that point, or as x approaches that point, exists and is the same limit that you got from the sided limit, because remember they are the same, they exist and they are the same. So that's what we kind of learned today. So you can see we are still getting there and there with the definition of the limit. We hope by the end of the limit you will be a brilliant student, and also work out as many problems as possible so that you get this concept clear. See you tomorrow.